So good morning, everyone from Chicago. Good evening if you're in Europe. I'm going to talk to you about a software package we've written. We call it larcv. The name came from liquid argon computer vision, so that CV is kind of harkening back to OpenCV namings. Oops. So I'm going to start with the why of this project. Maybe you've heard of this thing called machine learning and deep learning. Seems pretty cool. There was, some general consensus that if you could mix and match deep learning and high energy physics data, you could maybe get better science. I don't think this is a controversial opinion in this meeting, but I'll point out that this big plus sign is not always obvious from a computational perspective. A lot of these deep learning techniques are coming from big image analyses or text processing, and the data we process in physics is not always that. The challenge that we were facing in the neutrino world is that our data doesn't look like that image data. Typically, we have either really massive sparse images or something in 3D or point clouds or something like that. And the degree of sparsity can sometimes be incredible, less than 1% or 0.1% of voxels filled. And each example that you want to look at has a different degree of sparsity, so you don't have regular data. That's not an unfamiliar problem to this audience, but the challenge that we were facing is when you want to scale out and use, say, a supercomputer to train your model, sparse and irregular I/O is not a trivial pattern to manage, and it can become a bottleneck, especially at larger sizes. And you could just voxelize everything as dense data and compress it, but that turns out to be slow at scale too. Just to give you a sense of the data that this was built for, this is from one of the data sets from the short baseline near detector at Fermilab. This is called a cosmic tagger data set. It's just doing a segmentation task. But the background pixels in this, shown in gray on the right, are about 0.1 to 1% of each image. And the actual red target pixels are typically less than 0.1%. So the solution that we prepared, that we called larcv, fills this niche where you can take this data and get it to all of your accelerators on a supercomputer with low latency and at scale, so massive numbers of GPUs at a time, 2,000 or more. We wrote this package half in C++ and half in Python with bindings from PyBind 11. The approach we were going for there is dealing with a simulation package that isn't very accessible from Python and very slow from Python. So it helps to be able to pull data out of the simulation in C++, but have the same interface on both sides so that you can actually use Python when you want to do the cool machine learning stuff. And we wanted scalability and performance kind of by design. So we're not trying to hit speed records for I/O, but you need to stay fast. And one of my earliest physics professors always pointed out that, when you use a term like fast, it should be compared to what? So fast here means compared to however long it takes the rest of your algorithm on a GPU. So if your I/O is faster than that, you're going to be not noticing it. And we built this whole thing on open source and HPC friendly and Python friendly tools. So, NumPy, HDF5, CMake, and C++ via PyBind 11. And that's pretty much it. The GitHub link is there. You could also click the link in this, the PyHEP Indico page for the read the docs page and find the source code. The real thing that we developed was basically a data model for custom I/O layers. It looks similar to SQL, so it's basically turning your sparse data into tabular data. And instead of giant, 1,000 by 1,000 image reads of I/O, you're doing a small tabular lookup that you can parallelize with HDF5. And you don't have to know any of this to use the package. The user code is meant to be really kind of familiar looking and easy to use. Just some example data sets that I'll flash by. The data looks like this. We can store lots of different things that are useful for machine learning. Like here is an image with bounding boxes laid over it. Here's the same image, but looking at instance segmentation labels. So if you wanted to do clustering with machine learning, we can feed that data. And again, in 3D, image on the left is segmentation label bounding boxes versus the source voxels on the right. One of the advantages that we get from larcv is basically I/O performance. Compression is cheaper in sparse data compared to dense data, even for the same data sets, and even using all the best compression tools. And Because we use so much sparse data, we've added some basic, simple sparse manipulation tools, cropping, resizing, augmentation as you load it. And the user interface is the object level, so you don't really need to worry about all these storage details. And the under the hood layer written in C and HDF5 easily supports MPI. So when you want to go up to massive scales for readback, it's no problem. We did a couple performance studies. I took a couple data sets from neutrino physics. They're just listed here. You can see the occupancy, this right column is typically 10 to the minus 3 to 10 to the minus 6 for these data sets. That's how many voxels are filled out of how many voxels per image. So how many non-zero ones. It's typically very sparse. And we see that just going from reading back dense data to a dense array versus sparse data to a sparse array, like if you were going to feed it into a graph convolutional network, there's a 50 to 60% improvement in IO throughput. And it holds up as you scale up your mini batch size too. So your throughput really doesn't drop off as you get to bigger and bigger batches. And we also have a concurrency layer built in. So a lot of the data loaders in PyTorch, for example, use multiprocessing to pull up the next batch of data while you're using your current batch of data. larcv does this too. It's built on STD futures. So once your data is loaded and processing on the GPU, the next data is getting ready. So I've run this on one of our latest supercomputers. Even at 2048 GPUs, IO latency was about 10 to 20 milliseconds. And it scales out as well, as I mentioned. So this is going up past 10 to the 4 MPI ranks. You can see for all 3 of the data sets benchmarked, the throughput compared to the single node performance is basically linear with a few quirks. Notably, this supercomputer was bigger than one of the data sets in terms of total number of ranks. So as I got through a couple iterations of the data set, HDF5 caching kicked in, and I actually got a throughput speed up above a certain range. And in the biggest run we did, someone else stalled out the supercomputer and it took 20 times the standard time. So there's one point that dropped down. Is it useful to you, and is it stable and ready to go? I know all the developers here will admit that no project is ever quite finished to your own satisfaction, but you can't let perfection ruin progress. So larcv is ready for general use and stable for several years. There are features considered for future upgrades like point cloud data sets and direct to GPU loading, as well as integration with some of the framework data loaders to make it even easier for use. And just kind of as a summary, we have several developers led by Argonne National Lab, and we have a sparse data IO format. So if you want to use your weird and sparse data on supercomputing clusters and not have IO be a bottleneck, larcv might be useful for you. If you already have a solution, obviously, if it ain't broke, don't fix it. Some of our notable features is just the sparse data manipulation, concurrency with GPU processing, and really good weak scaling. So, more than 16,000 ranks and global batch sizes of more than 250,000 sparse images took just 20 milliseconds. So things that were unmanageable before in dense format, particularly in 3D, are now manageable using this package. So thank you. Happy to take any questions.
Yeah, thanks a lot. That sounds very interesting. And I think maybe partially my question is already answered, but yeah, my question would be a bit, how does this compare to awkward array and also to graph neural network libraries? So mainly what's the additional thing it can do that those can't?
Yeah, so I'm not a user of awkward array, and I can't really speak to the pros and cons of various ones. So if you have a workflow in awkward array that's working for you, awesome, go for it. One of the things that this offers is it's generally built with supercomputers in mind. So everything is built to be scalable. I don't know how scalable awkward array is, but you can take larcv and go run it on Summit or Frontier or Polaris or Aurora next year, and it will work up to the scale of the biggest supercomputers that are out there. Does that answer your question?
Yeah, maybe a bit. And I think what maybe there's also a point, these sparse to dense operations, yeah, when I tried to do this, was usually a little bit manual to do that. When you have some kind of sparse or checked representation, and then need to put it back into a dense one in an efficient way, that usually was a bit cumbersome.
That's all built in here. You can always go from sparse to dense and from dense to sparse here.
Okay. Yeah, sounds very, very interesting. Thanks a lot.
Yep.